Okay, so that was with a single variable. And usually when we do classification, we've got more than one variable. So now we're going to go to multivariate Gaussians. So here's a picture of a Gaussian density when we've got two variables. So it's one of these fancy-looking three-dimensional plots.
It's beautiful.
Beautiful, isn't it? The height's color-coded. Could you make a plot like this, Rob?
I could try, and then you'd criticize it. You do criticize it.
Actually, the beautiful thing is that R made this plot with very little work from us. So there's two variables, x1 and x2, and you can see the Gaussian density in 2 dimensions looks like a Bell function. And this is left-hand case is the case when the two variables are uncorrelated, so it's just really like a bell. And the right-hand case is when there's correlation, so now it's like a stretched bell. You can see there's positive correlation between x1 and x2. So those are pictures of the densities. The formula for the density doesn't look nearly as pretty, and here it is over here. And it's somewhat complex.
Well, you should go over this in great detail now. Excruciating detail, please.
I have a feeling that's a hint not to go into it in great detail. Anyway, this is just a generalization of the formula we had for a single variable. This here is called a covariance matrix, and it's if you stare at this formula and you stare at the previous formula, you'll see that there's somewhat similarities, especially if you know a bit of vector algebra. If you go through the simplifications, if you know your linear algebra, you can form and do the cancellation similar to what we did before. You can form the discriminant function, which is given over here. And it looks complex, but important thing to note is that it's again linear in x. Here's x alone multiplied by a coefficient vector, and these are all just constants. So this again is a linear function. If the math's beyond you, don't let it bother you. This is a linear function, and we'll make that more clear a little bit later on as well, that this is a linear function. In fact, we make it clear right here. It might look complex, but this can just be written in this form over here. Okay, it's a linear function. So this ck0, so this is a function for class k. ck0 is built up of all these pieces over here, and then each of the coefficients of x1, x2 up to xp come from this part over here. Remember, x is a vector in this case, and so you can expand this expression and get this term over here. And I think I forgot to mention it before. What the idea of the discriminant function is, you compute one of these for each of the classes, and then you classify it to the class for which it's largest. You pick the discriminant function that's largest. Well, we can draw other nice pictures for discriminant analysis, similar to the one-dimensional picture we drew before. So here we've got 2 variables and 3 classes. And we can't, instead of showing those density plots, what we do is show contours, in this case, of the density. So here's the blue class, and we're showing the contour of a particular level of probability. Okay? For the blue class, for the green class, and for the orange class. Okay? And lo and behold, and the decision boundary is the dotted line here. And it's really very pretty. It shows you where you classify to blue versus orange, and it's exactly where it cuts, where the line goes exactly through the points where the contours are cut. Both for the orange to blue, for the blue to green, and for the green to orange. And you can see they all meet in the middle over here, right in the center over here. And so if you knew the true densities, it would tell you exactly, and in this case they're Gaussian, you'd get the exact decision boundaries. Again, these are called the Bayes decision boundaries. These are the true decision boundaries. Now, of course, we don't, but we go ahead and estimate the parameters for the Gaussians in each of the class using formulas similar to what we had before, but appropriate for this multivariate case. So in this case, we're going to get the mean for x1 and x2 for the blue class, it's about there. For the green class with data points about there. For the orange class, say there. And then we plug them into the formula. Instead of getting the dotted lines, we get the solid lines. And in this case, it's remarkably close. Now, these data were actually generated from a Gaussian distribution, so it's not too surprising that we got close. But with relatively few points, we get decision boundaries that look pretty close to the real ones. You cannot learn about discriminant analysis without seeing Fisher's iris data. It's maybe one of the most famous data sets around. It studies 3 species of iris. These species are Setosa, versicolor, and virginica. And they're color-coded in this scatterplot matrix, again, with 3 colors in this case. And there are 4 variables that are going to be used to try and automatically classify these 3 classes. Sepal length, sepal width, petal length, and petal width. So these are aspects of the flower. And there's 50 samples in each class. Now, if you look at these scatter plots, you can see that there's some really good separation. For example, in this plot of petal length and petal width, the blue class really stands out as being different from the other 2 classes. They seem to be more confused in some of the plots, but and in some there's slightly more separation. But the idea here is to use all these variables together to come up with a discriminant rule and classify. And so this was a motivating example that Fisher used in his first description of linear discriminant analysis. And in fact, it's often known as Fisher's linear discriminant analysis. Importantly, what comes with discriminant analysis is a nice plot. Right? In this previous picture, there's 4 variables, so we showed a scatterplot matrix of each variable against the rest. But it turns out that there's a single plot that captures the classification information for all of these variables. And here it is. And I've got discriminant variable 1 and discriminant variable 2 as the horizontal and vertical axes. And it turns out these are linear combinations of the original variables, but they're special linear combinations. And when you plot the variables against these 2, you see really good separation. And these arise from actually performing the linear discriminant analysis. Because you've got 3 classes, what Fisher's linear discriminant analysis is really doing, or Gaussian LDA is really doing, is it's measuring which centroid is the closest. But it's measuring it in a distance where it takes into account the covariance of the variables. But ignoring the covariance for a moment, the distance, the 3 centroids actually lie in a plane, a subspace of the 4-dimensional space. And it's really distance, so if you have 3 points, they span a 2-dimensional subspace. And that's essentially what we're plotting here is the 2-dimensional subspace. So seeing which class is closest really amounts to distance in that subspace. And that leads to these nice low-dimensional plots. And so we have 3 classes here. We can make a 2-dimensional plot, and it captures exactly what's important in terms of the classification. And when we have more than 3 classes, we can still find 2-dimensional plots. But in that case, it doesn't capture all the information, the 2-dimensional plot, but we can find a best 2-dimensional plot for visualizing the discriminant rule. And that's another important reason why linear discriminant analysis is very popular for multi-class classification.
So keep in mind, this case we had only 4 features, 4 variables, right? And
yes.
Discriminant analysis was a very attractive method, but imagine we had 4,000 features, right? Then in ingredient, what we just did was the covariance matrix. We had to plug in an estimate of the covariance matrix.
Yes.
Right? If you had 4,000 features, that covariance matrix would be of size 4,000 by 4,000.
Yes, that's a great point, Rob. And we just can't carry out discriminant analysis without other modifications if the number of variables are very large. And we're going to talk about some ways of doing that. And later on in the class, we'll talk about even more ways. We've talked about discriminative functions, which is telling you how you classify. But it turns out that you can turn these into probabilities very easily. And here's the expression over here. And So remember, we got the decays by doing a lot of simplification. Well, it turns out that those simplifications and cancellations hold exactly for computing the probabilities. So in other words, those expressions we had earlier for computing the probabilities, let's go back to it. For example, here's an expression here that's used in computing the probabilities. Where is it? This is the expression for the single variable case with all these constants in that all the cancellation happens, and we get to this nice simple expression over here, which just involves the discriminant functions. Okay? So you can see if you can actually show that as well. It's not that hard to show. And so we can, not only does discriminant analysis give us a classifier, it also gives us the probabilities. When k is 2, we'll classify to class 2 if these probabilities are bigger than 0.5, else to class 1, just like in logistic regression. Here's the credit data. And we produce, in this case, a misclassification table. Okay? So this table has got, along the horizontal, it's got the true status. So it's a true default status, which is no or yes. You can see we had 10,000 samples in the credit data. And in the vertical, we've got the predicted status, no or yes. So of course, we'd like everything to lie on the diagonal. It turns out we got a lot of the no's right, and not that many of the yeses right. So on the diagonal is what you got correct. On the off diagonals is what you got incorrect. Nevertheless, overall, we make 2.75% misclassification errors here. Okay, so this is called a confusion matrix. It tells how well you did. Now, there's some caveats. This is training error, right? We fit the rule to these data, and now we see how well it performs on these data. So we may be overfitting. Well, we've got 10,000 training samples here, and we've only fit a handful of parameters. So it's very unlikely in this case that we're overfitting. For small training sets, that would be an issue, and you need to have a separate test set. Another thing to note is that although 2.75% seems a really good misclassification rate, if we just use a very naive classification rule and said, I'm going to always classify to the largest class, in other words, classify according to the prior, we'd only make 3.33% errors, right? Because there's a predominance of no's in this data set, right? The total number of no's is 333 out of 10,000, right? So this we call the null rate, and so you always use bear in mind the null rate when getting excited about a misclassification error rate. The other thing to look at, though, is you can break the errors into different kinds. So of the true no's, we make 0.2% errors. So we hardly ever misclassify a no. But of the yeses, we make a whopping 75.7% errors. Right? So the errors are very lopsided in this case. And that's maybe not such a good idea. So we break down these errors into finer categories. So we call the false positive rate the fraction of negative examples that are classified as positive, right? So they're false positives. In that case, that was the 0.2% in this case. And the false negative rate, that's the fraction of positive examples that are classified as negative, the 75.7% in this case. Now, we produced the classification table by intuitively correct, classifying default as yes if the probability of default was bigger than 0.5. Okay? But it gave us this very lopsided false positive and false negative rate. In some cases, especially for these kinds of screening examples, you may want to change the false positive and false negative rates and skew them to one side or the other. Right? And you can do this by changing this threshold. Instead of classifying, in this case, to default if it's bigger than 0.5, you can change the threshold and maybe make the threshold, in this case, smaller, so that you can catch more of the high-risk cases for default. Okay. And so here we've done it as a function of the threshold, and we've just looked at negative thresholds, or decreasing thresholds. Okay. And so in this plot, we've got in black the overall error rate. In orange, we've got the false positive rate, and in blue, we've got the false negative rate. And so as we decrease the threshold, the false positive rate increases, because now we're going to classify more and more negatives as positive. But it increases very slowly, you'll see, for a long part of the threshold going down, the decreasing threshold, the false positive rate doesn't increase very fast. Of course, the false negative rate increases as we do that. And so even at point 1, right, the false positive rate hasn't increased a huge amount, and the false negative hasn't increased a huge amount, but we've changed the balance of classification. And so you can change the threshold. Well, you can capture that change in threshold in what's known as an ROC curve. So what this shows is the two error rates, in this case false positive rate and true positive rate, as we change the threshold. Okay, and we'd like the false positive rate to be low and the true positive rate to be high. And so this ROC curve traces out as we change the threshold, and the 45-degree line is the kind of no information line. And what you'd like is this curve to be right up as far as possible into the top left-hand corner. So if you had a true positive rate of 1 and a false positive rate of 0.
So if you flipped a coin, you'd be on the straight line.
You'd be on the straight line. Okay? And so this is a single curve that sort of captures the behavior of the classification rule for all possible thresholds. And you can compare different classifiers by comparing their ROC curves. Okay? And to summarize it even more, we sometimes use the area under the curve, or AUC, which captures the extent to which you're up in the northwest corner. And higher AUC is good. Okay?